Today, we're looking at a paper with a huge claim in its title. Error-free linear attention is a free lunch. It's from researchers at Nanyang Technological University and Fudan University, and they're tackling what is maybe the single biggest blocker for LLMs today, the quadratic cost of attention.
It's a massive problem. I mean, if you're trying to process long documents or run these really long RL trajectories, you just hit a wall with that all LOD complexity. It's just crippling.
And we've seen attempts to fix this before, right? Linear attention methods like DeltaNet gave us that efficient LD$ scaling, but they had this hidden flaw.
Numerical flaw, yeah. Those methods were built on what's called explicit Euler discretization. It's the simplest possible approximation, but it means you get this unavoidable error buildup. It's unstable.
So this is where error-free linear attention, or EFLA, comes in. Their whole approach is different. They look at attention as a continuous time system, an ordinary differential equation, and instead of approximating, they found the exact analytical solution.
And this is the magic trick. They found a kind of structural loophole. They realized the dynamics matrix has a very specific rank 1 structure, and because of that, they can compute this exact solution, which is basically the same as an infinite order Runge-Kutta method in linear time.
You get the precision without losing the speed, the free lunch.
Exactly. And the results back it up. It's way more robust, and it beats the older methods on language modeling, especially on reasoning tasks.
Okay, let's dig into that. Let's start with the motivation here, because this is a really practical problem. We see LLMs becoming these complex agents, using tools, dealing with huge contexts. Why does standard attention just fall apart in those cases?
It's purely a computational cost issue. When you have quadratic complexity, doubling your sequence length means quadrupling your compute and memory.
It just explodes.
It explodes. So if you want to feed it a 50,000 token document or have an agent that thinks for 1,000 steps, standard attention makes that almost impossible, or at least incredibly expensive. We just have to have linear scaling.
And this idea of connecting sequence modeling to dynamical systems isn't brand new, is it?
No, not at all. Works like Mama 2 and DeltaNet already made that connection. The core idea is that you can think of linear attention like a physical system. You have a memory state that's exponentially decaying. That's the forgetting part.
And then you have new information coming in.
Exactly, an input injection. That's the model learning from the new token.
So DeltaNet took that idea and framed it as an online learning problem.
Right. They basically said, let's treat this as online gradient descent on a reconstruction loss. And when you do the math for that, you naturally end up with the classic delta rule update.
Which is that formula, Sioki ILAT ST1 plus Peta ATVT top.
Yes, and it's great because it's algebraically neat, it's fast, and it gives you that linear time complexity.
We thought we were done, problem solved. But the authors of this paper spotted the catch.
They did. They realized that this delta rule, as nice as it is really just a mask for the most basic, lowest fidelity numerical integration method there is.
Which is the explicit Euler method you mentioned.
Exactly. If you write down the true continuous dynamics as an ODE, that delta rule is nothing more than the first order Euler approximation of it.
So it's like you're trying to predict a whole trajectory based on just the very first step. Why is that so bad for something like an LLM?
Well, Euler's method has a local error of betat2, which adds up fast. But the bigger problem is that it's numerically unstable, especially when the system becomes stiff.
Okay, what does stiff mean in this context? What makes an LLM's dynamics stiff?
Stiffness happens when you have things happening on wildly different time scales. For an LLM, that can happen when a key vector suddenly has a huge magnitude. It's a high energy input that forces the memory to change drastically and instantly.
And Euler's method just can't handle that jump.
It can't. It overshoots, it oscillates, and the whole internal state can just, explode or collapse. It's fundamentally unstable for those kinds of inputs.
Which explains all those weird heuristic fixes we've seen in other models, like custom decay factors or weird gating functions.
Exactly. Those are all just band-aids. They're engineering patches trying to stabilize a mathematical foundation that is fundamentally unstable. You're just damping the error, not removing it.
So to really solve it, you need to move to a higher precision method, like a Runge-Kutta method.
Right. Instead of one slope estimate, an RK method takes multiple peaks to get a much more accurate estimate of the trajectory.
And the authors here thought, well, why stop at RK2 or RK4? Let's just take it all the way.
Let's take the limit as the order no dollar goes to infinity. And when you do that, the math works out beautifully. The power series converges to the exact analytical solution of the ODE.
Which is that equation with the matrix exponential, A-Betech.
Yes. That equation is the error-free, continuous blueprint for how the attention memory should evolve. No approximation, no discretization error. It's the ground truth.
Okay, that sounds perfect. But this is where these ideas usually die, right?
Yeah.
Because computing a matrix exponential for a big matrix it's horribly expensive, usually $1 to $3.
It's a total deal breaker. If your hidden dimension dollars is, say, 2048, then dollar cubed is enormous. You'd just be trading one bottleneck for another, even worse one.
So what was the aha moment? How did they get around that?
The insight is so specific and so crucial. It's that the dynamics matrix isn't some random general matrix. In linear attention, it's defined as $TT.
It's a rank 1 matrix.
It's a rank 1 matrix, and that specific structure is the key that unlocks the whole thing. It's the free lunch.
How does being rank 1 help? What does that do to the math?
It has this amazing property. When you raise $8 to any power, say $8, it doesn't get more complicated. It just becomes a scalar multiple of the original order.
Wait, really? So a squared is just a number times a dalar?
Precisely. It's almost idempotent. The formula is a damn $1, where that lambda is just the squared norm of the key vector, a simple scalar.
So you can take that infinite Taylor series for the matrix exponential.
And it just collapses. The entire infinite series simplifies down to this incredibly compact, closed form. It becomes the identity matrix minus a scalar factor times 80 taller.
Something you can calculate in no Taylor time.
Exactly. The ALD3 barrier just vanishes.
That's incredible. But what about the other part, the input integral? That still looks pretty messy.
That simplifies even more cleanly, believe it or not. Because of that same rank 1 property, the matrix as times the input term, old die, just becomes the scalar lambda times build dot.
So the matrix part of the dynamics just drops out of the integral.
It does. You're left with a simple integral of scalar functions, which has a clean, trivial solution. So you combine that with the simplified matrix exponential, and you get the final, elegant, and perfectly tractable EFLA update rule.
And you've done it. You have an update rule that maintains the LD2 complexity we need, but it captures the exact continuous dynamics. No more error.
That's the free lunch right there. But, the theory is one thing. Does it actually hold up in practice?
Let's look at that. They put it through some serious stress tests, starting with sequential M&S, which is a long sequence task. They tried things like input dropout and adding noise.
But the really telling one was the out-of-distribution intensity scaling.
What's that?
That's where you artificially amplify the input signals. You're basically creating a worst-case scenario for Euler's method. You're intentionally making the system as stiff as possible.
Then what happened?
DeltaNet just collapsed. Its performance fell off a cliff, which is exactly what the theory predicts. That's the numerical instability in action.
The state explosion.
Yep. But EFLA just sailed through. It maintained high accuracy even when the inputs were scaled way up. The exact solution has this kind of built-in natural saturation mechanism. It knows how to handle high-energy inputs without blowing up.
Okay, so it's robust. What about the main event? Language modeling.
Looking at their main results table, for both the 340 million and 1.3 billion parameter models, EFLA is consistently better than DeltaNet.
I noticed the perplexity was significantly lower on the Lambda dataset.
Which is a big deal because Lambda is specifically designed to test long-range context understanding. And on reasoning tasks like bool-q, the accuracy jump was even bigger. Better memory fidelity is translating directly into better reasoning.
So if the memory is better, what's the mechanism? You mentioned that scalar key norm, lambda, before.
Right, lambda AT22. That little scalar turns out to be the master controller. It acts as a dynamic spectral gate.
How so?
The term that controls memory decay is embedded lambda. So think about it. If you get a really strong, important input signal, lambda is large. That makes the exponential decay extremely fast.
So a strong signal essentially says, hey, I'm important. Clear out the old memory in this slot and pay attention to me.
That's a perfect way to put it. It's an implicit, mathematically grounded forgetting mechanism. And conversely, if the input is weak, lambda is small, the decay is very slow, and the model holds onto the old memory. It's so much more elegant than a hard-coded heuristic.
Now, for anyone actually training these models, there was a really important practical detail in the appendix about the learning rate.
Oh, yeah, the vanishing update problem. Because EFLA's update is bounded by this soft gating term, its magnitude is naturally sublinear. As the model gets closer to converging, the updates get smaller and smaller.
So it sort of dampens its own learning signal.
It does,
Yeah.
which means if you try to train EFLA with the same learning rate you used for DeltaNet, you might not get great results.
You're underpowering it.
Exactly. The paper points out that it structurally requires a larger global learning rate. They suggest something like $3 times 10 $3 to counteract that dampening and really reach its full potential. That's a key detail that comes straight from the math.
Let's put this into the broader context of other architectures. What about state space models like S4 or Mamba? They also start from continuous time systems. Why didn't they find this error-free solution?
The key difference is the structure of their A matrix. In SSMs, they deal with general full-rank A matrices. And for a general matrix, there is no known way to compute the matrix exponential in linear time. It's intractable.
So they're forced to use approximations.
They have to. They use things like the bilinear transform, which is a very good RK2 order approximation, but it's still an approximation. It's not error-free.
So EFLA's breakthrough is entirely dependent on that special rank 1 structure that's unique to linear attention.
100%. That rank 1 property is the loophole that let them jump straight to the RK infinity limit. Without it, they'd be stuck with the same computational trade-offs as everyone else.
And from an engineering perspective, it's a clean swap. The final update formula looks a lot like DeltaNet's.
It has the same algebraic structure, yeah, which means you can use all the same hardware-efficient tricks like chunk-wise parallelism. It really is a drop-in upgrade for numerical fidelity.
So this really proves that you can have both. High fidelity, error-free attention, and linear time complexity. You just have to look very closely at the underlying math.
It's a beautiful piece of work. It really bridges numerical analysis and neural network design in a very powerful way.
A fantastic result, closing a long-standing gap between speed and precision.
It really is. And it makes you wonder, doesn't it? I mean, EFLA, it worked because this specific rank 1 structure in linear attention happened to provide this free lunch, an exact closed-form solution. So the provocative thought is, what other complex dynamical systems are hiding inside our neural network architectures? Are there other components, maybe with different low-rank properties or other algebraic structures we haven't even thought to look at, that also have these hidden, analytically perfect, error-free solutions just waiting for us to find them?